Let's get some facts. 37% of you aren't subscribed to this channel. That's almost 4 out of 10 just freeloading the alpha. So come on, hit subscribe and I promise to keep leveling up the show with the best guests and the juiciest insight. Go on, do it now.
Hi, I'm Kevin Bowers and Chief Scientist of the Jump Trading Group. This is our 4th consecutive time presenting at Breakpoint. Thanks for having us back. The title of today's series of talks is When Firedancer. Richie Patel, Philip Taffet, and Michael McGee will be delivering additional talks on stage today. Anway D will be helping to run the live demos here at the end. Today, I will give some introductory remarks to cover what we've been up to since Breakpoint 24. Then Richie will talk about fast snapshot loading. Philip will talk about fast replay. And last, Michael and Anway will do some live demonstrations. On a validated podcast in 2024, Austin Federa asked how far along we were getting to mainnet. I answered this was less a question about technical capability than it was about choosing a comfort level where we felt it was safe to deploy so that users would have a boring experience. In a world where developers are encouraged to move fast and break things, this sounds counterintuitive. But the only time users get excited about infrastructure is when that infrastructure breaks. Users aren't often even aware they depend on some infrastructure. Most users interact with infrastructure through applications that rely on it. The recent failures of traditional cloud providers and the resulting far-reaching knock-on effects, including across many parts of the crypto ecosystem, demonstrate this quite dramatically. To provide a credible alternative to big tech and traditional finance, technologies like blockchain need to be more reliable, more predictable, and more affordable to be run by operators, trusted by developers, and subsequently adopted by users. The last thing in the world we wanted to do was jump the gun on deployment. We knew that if a mainnet Firedancer launch was exciting, it would almost certainly meant the launch didn't go right. That kind of excitement is not a good thing. That kind of excitement wouldn't just devalue all of the effort we put into Firedancer, it would devalue the whole ecosystem that wanted and needed a truly independent second validator. As I put it on Validated then, my dream was to go live on mainnet and nobody notice. We view deploying Firedancer as akin to upgrading a utility. Consider the power grid. Users do not and should not get excited when a generator comes online. They just don't want brownouts. Users do not want to have an exciting experience when they flip a light switch. They just want the light to turn on. Users do not want to have an exciting experience when they open their utility bill. They just want their power to be affordable. We believe that upgrades to Solana should be just as uneventful. Unsurprisingly, we are heavily focused on minimizing risk to on-chain activity as we move Firedancer from the lab to the real world. There are 2 components to this risk. One is the probability things don't go right. We've been driving this down with ever more testing, auditing, fuzzing, and so forth. The other is the impact if things don't go right. Here, the community has grown faster than we could have hoped when we started the project. But this also increases the pressure to get it right the first time. This is a good problem to have, a great problem even. Consider the opposite, a shrinking community huddled around a stagnant protocol. Would it matter if an upgrade doesn't go right? Because we often see confusion between Firedancer and Firedancer, it is worth covering the difference and how it arose from our development philosophy. Recall computer science decision paralysis. When nothing is optimized, Amdahl bottlenecks mean there's no immediate payoff to any one optimization. Everything must ultimately be optimized, and most of the benefits are seen when that last bottleneck is removed. Recall Amdahl Street justice. When we throw in latency and bandwidth constraints, everything must also be in the right place at the right time. That is, in addition to optimizing everything, we must streamline the data flow. Fortunately, the protocol is designed for parallelism and conceptually has a streamlined data flow through a validator. This means we can isolate agave components and incrementally replace them with independently developed ones. We call these hybrids Frankendancers, and this approach is very practical. As the protocol and agave evolve independently, we naturally keep in sync with protocol updates and code changes. The resulting validators are composed of documented and standardized tiles that others can replace to make their own validators. We get community participation, release, and operational experience during development. Today, Frankendancers use our kernel bypass networking, core-to-core communications, quick implementation, signature verification, block packing, parallel transaction scheduling, parallel transaction execution, proof of history, read-Solomon encoding, turbine block distribution, etc. The main remaining agave components are the Solana bytecode interpreter and tower consensus. Ongoing work is mostly putting the last pieces into place, and testing and polishing, and testing and auditing, and testing and fuzzing, and testing and documenting, and so on, to realize the Foundation's primary goal of having a second, completely independent validator, a full Firedancer. At Breakpoint 2024, we showed this timeline that covered key milestones up to that point. We officially announced the open secret that Frankendancer was live on mainnet, and Firedancer was live on testnet. At the time, we expected to spend 2025 doing the grinding necessary to give the boring experience necessary to compete with big tech and traditional finance. Because this doesn't generate obvious milestones, we were worried there wouldn't be much else to show on a timeline like this. But we were wrong. Frankendancer usage grew dramatically over the year. At Breakpoint 24, Frankendancer 0112 was live on mainnet with a tiny amount of total stake across a couple of validators. We had been running it on mainnet on and off internally since mid-2024. By May, Frankendancer had over 5% mainnet stake. Multiple operators were running it with around 30 validators. Frankendancer is now up to version 0806 and has been fluctuating between roughly 20 to 30% of mainnet stake. Multiple operators are running it with around 175 validators. Operators were even discouraged from migrating even more stake. Frankendancer's current level is adequate to get real-world production statistics necessary to tune the full Firedancer while minimizing ecosystem risk. That is, we walk the walk. Our goal has always been to foster the development of a high-performance, enterprise-grade ecosystem with multiple independent validators. A big part of this is developing Firedancer in public to encourage the community to adopt the types of technologies necessary to compete with big tech in traditional finance. In previous talks, we showed blockchains could be accelerated by using the same advanced hardware network techniques deployed by big tech and traditional finance. One of these was at an offsite with folks from Anza and Foundation in mid-2024. I was asked to give some opening words that sprawled into 4 stories about the technical challenges created by community growth. We called these the amazing stories of Frankendancer. One of the stories was a gigabits per second attack is a you problem, a terabits per second attack is a we problem. The point of this story was, even if you had an infinitely fast validator, it did not matter unless you also had a fast physical network. We described how to distribute a validator's functionality into 2 or more logical rings connected by a community multicast capable wide area network to overcome Amdahl Street justice and get everything in its right place at the right time. A few months later, 00 built this. We contributed some of the FPGA technologies from our demos at Breakpoint 22 and 23. We also contributed some of the same network capacity we used for our 1 million transactions per second global network demo at Breakpoint 24. Throughout the year, we gave back to the community and are happy the community has adopted our testing and conformance suites and to prove reliability and create additional independent validators. Oh, and one more thing. Firedancer is live on mainnet. It's been hiding in plain sight. Just like last year with Firedancer, this is a bit of an open secret, in part because Michael and Anway demoed it a few days ago at Block 0. Firedancer started voting on mainnet in July and producing full blocks on mainnet in October. Full Firedancer is currently running on a handful of our validators with a tiny amount of stake. It has accumulated over 100 days mainnet runtime across 3 validators, produced over 50,000 mainnet blocks, and landed over 20 million mainnet votes. Just like last year, we expect the number of operators and validators using the full Firedancer to grow in the coming months as we get more soak testing, complete external audits, and start encouraging other operators to upgrade. In short, this year, a significant fraction of mainnet stake migrated to Firedancer, a significant fraction of mainnet stake migrated to 00. We started running full Firedancer on mainnet, and nobody noticed. Dreams do come true. With that introduction out of the way, each time we present at Breakpoint, we try to have an underlying theme. For example, at Breakpoint 23, the theme was how the speed of light creates a natural parallelism hierarchy. Each talk covered an innovation we made at a level of the hierarchy. We will follow the same pattern as Breakpoint 23 this year. This year's theme was inspired by another amazing story of Firedancer: big snapshots, slow recovery. The point of that story was, even if you had an infinitely fast validator, it did not matter unless that validator could start up fast. We chose this theme because it is a nice example that we really do have to optimize everything. Startup doesn't even seem to be in the critical path, so it is easy to neglect in development. But it is critical for real-world success. Like Firedancer's development followed the data flow through the leader pipeline, today's talks will follow the data flow through startup. Now, in the past, we've talked a lot about high-performance computing and high-performance networking. But we haven't talked much about high-performance file I/O, compression, and databases. And that's what snapshot processing is all about. So first, Richie will talk about how to optimize loading a mainnet snapshot. Then Philip will talk about optimizing transaction replay. Because the transactions to catch up at startup can be streamed much faster than real time, accelerating replay accelerates startup. But it does more than that. A validator spends most of its time replaying and voting on blocks from the current leader. Accelerating replay allows Firedancers to vote in a timely manner while increasing chain capacity. Then at Block 0, 2024, Michael and Philip had an hour slot for a talk and live demo. The demo was to procure a node from AWS, download Firedancer from GitHub, build it from source, and then fire it up on testnet. While this all worked, the demo had barely caught up to real time by the end of the talk, and they weren't lucky enough to get a leader slot in the remaining time. This year, Michael and Anway are going to do a similar demo. But this time, they're going to use the full Firedancer on mainnet to show the impact of these optimizations, plus many others that we do not have time to cover. Now I'll disappear and turn the stage over to Richie.
I'm Patel, and I'm an engineer on the Firedancer team. My talk today is about fast startup of a Firedancer validator from a snapshot. Cold starting a validator is actually a pretty tough engineering challenge. So here's a quick overview of Solana's mainnet state. We have about 1 billion small accounts that together make up 0.5 terabyte of data. We have to download that data, unpack, and index it as fast as possible, because before we can replay the first transaction, we have to have all of that data local. An earlier version of that code about a year ago took about 20 minutes just doing the cryptographic verifications of that data. And if you took an average cloud storage provider, it would take you about 40 minutes to download all that data. But what if you could do all of that in under a minute instead? I mean, we want our operators to come up quickly, since every minute of downtime costs them money and is bad for the network. So let's step a bit back. How fast can the hardware actually go? Since we're at the login stage, some of you might recognize this thing. This is a typical Solana validator. I found this one in our Chicago office, and there's about 1,000 of these that together make up Solana. Let's quickly pick it apart. It has a ton of memory, it has an awesome modern CPU, often latest generation available, and the storage in this box is equally impressive. Just saving the copy of all of that account data would just take 10 to 20 seconds if you compress it. The network interface is surprisingly even faster than this, so I'm going to quickly admire this box. But this is not even the top of the line box. I mean, Solana's operator community competes who can rack the fastest hardware, and this is one of the things I love about Solana. So we can say we clearly have fast enough hardware to start up a validator quickly, so maybe the problem is the network. Let's look at what a validator is typically connected to. We probably have a bunch of neighbors in the same rack, or zooming out the topology, data center has multiple racks, and the metro area typically has multiple data centers. And empirically, we've seen that for point-to-point transfers between any of these two boxes that might be in the same metro, we can get speeds of up to 50 gigabits a second. It gets a bit tricky downloading large amounts of data from remote locations, but Solana at this point is a massive global network, so there's probably a major cluster that hosts the data you need not far away from you. And if it is, physical infrastructure networks and community projects have come a long way optimizing snapshot download speeds. So we can also conclude, the network is likely fast enough, we have fast enough hardware, it's clearly a software optimization problem. So here comes the fun part. The next 10 minutes will be a high-performance computing crash course going through each step of the snapshot loading pipeline, and hopefully we'll give you a behind-the-scenes look of how Firedancer thinks about performance problems. So here's the whole pipeline visualized. You can kind of see the gray boxes as anything to do with data movement. Data flows from left to right, so we download, decompress, and index accounts. We also have to cryptographically verify them, which are the blue boxes. And then finally, we have to store that data so it's useful for transaction replay in the green parts, which is our database. There's a really cool property here, and this is sort of borrowed from our network stack work. Every step of that pipeline runs concurrently in different processes pinned to CPU cores. All data flow is explicit and streamlined. So we practically have no shared state between tiles, helping us to divide up that big problem with just loading a snapshot into independent subtasks that we can tackle individually. Another very important property of this is that since you have this nice and streamlined pipeline, there's practically only ever one tile that bottlenecks the overall throughput. So this is literally the bottleneck of the pipeline. Internally, we like to call this a game of whack-a-mole, where we hammer away at the slowest tile until the problem pops up somewhere else. This might seem super obvious, but actually what you find a lot with apps that have complex thread concurrency is that you spend half an hour looking at some weird performance profiler, trying to find out the part that makes it slow. But here, we spend all of that time just actually doing the optimizations because we kept the pipeline simple. So let's go through the pipeline. Starting with downloading and I/O, which are pretty simple. These are all about streamlining physical data movement and avoiding round trips. We've spent plenty of time talking about Firedancer's network stack on previous conferences, so it's the same thing again. Use kernel offloads, zero copy I/O, get the network adapter to place data in pre-registered buffers with minimal CPU involvement. This gets us up to line rate data transfer speed. As I said, I'll skip through this a bit, but I'd love to talk about this after the talk if anybody would like to learn more about it. I/O is similar. We need to find the right incantations, of course, to kernel APIs to bypass slow cache algorithms, program the NVMe device to fetch data on its own from DRAM with again, minimal CPU involvement, and we're up to hardware speeds. What's a bit more interesting, though, is the next step, which is decompression. Solana accounts are sent over the network compressed, which reduces bandwidth requirements about 4x. We have to uncompress all of these accounts before we can load and verify them. The tape here is meant to visualize the compressed stream as seen on the wire. This compression stream is in the Z standard format by Meta, and internally is made of these small blocks here. Each block is uncompressed and then yields a chunk of decompressed data. But there's a very painful property, which is actually necessary part of this compression format, which is that each compressed block has a sequential dependency on the previous block. This means that we have to process blocks one by one. Our decompressed output rate with a single thread is about 3.5 gigabytes a second, which might seem cool at first, but it's actually way slower than our network interface, and we need to go 10x faster. So this is our first real problem. To understand this a bit more, let's kind of dig into what a snapshot file looks like on the wire. We see that the entire compressed snapshot is in one Z-standard frame. A Z-standard frame is a sequence of sequentially dependent blocks. Solving this problem on the compression side is literally a single line or letter change. The parallel Z-standard compression strategy splits the input in multiple frames. These frames can then be processed independently, which is very useful for the decompressor. The compression ratio penalty is tiny, with the snapshot only growing by about 0.2% in size. So looking at this diagram again, now we have threads hammering away independently at multiple frames. So if you want to 10x the performance, that just means 10x in the amount of threads. With that, we have the decompression part solved too. Next, we have to index each account. Recall that we need random access to all of these accounts, so we need to build a global index for these built-in accounts. In Firedancer, the account index is a giant hash map stored on DRAM, spanning about 100 gigabytes. The indexing algorithm is actually quite simple at a high level. It's pictured here by this pseudocode snippet. We hash each key to a place in the hash map, which is statistically random. Check if the account exists, otherwise insert it. But wait a minute. It's actually crazy slow. So we have this 4 gigahertz CPU, and it can theoretically do 4 billion operations a second, yet this algorithm just does 10 million in the simple case, or like the naive implementation. And this is a story about DRAM memory latency. And mind you, there are no disk accesses here. Turns out that since we are doing sparse random accesses over a large amount of memory, statistically, every memory access is a cache miss. So physically, those bytes have to travel all the way from DRAM to the CPU. We fetch the data from a faraway place. This physically takes 100 nanoseconds per iteration. And we do not have any concurrency at this step. This is too slow. While we cannot change memory latency, this is a physics problem, we can use a trick to get the CPU to read multiple elements from memory at once. Empirically, doing 8-way parallelism works best. And this, gets us an 8x speed up. Under the hood, we use a trick called instructional parallelism to do this. We use this throughout Firedancer. Looks kind of like this in assembly. So this is x86 assembly in Intel syntax, meaning you read it right to left. Each of these instructions takes some bytes in DRAM and then moves them to a register. And by laying these instructions out close to another and avoiding data dependencies between them, under the hood, the CPU frontend can dispatch all of these instructions at once and then run them in parallel under the hood. This pattern is also called a memory gather. There's a funny anecdote. We don't want to put random assembly blobs in our code base because this would be absolutely unmaintainable. So in high-performance computing, you do this thing a lot where you re-implement it in readable code, and then you recompile it and tweak the code until you get the produced assembly to have the properties you want. In this case here, you can see the 2 big red arrows pointing to the slow instructions that we want to run in parallel. In any case, this significantly improved our indexing throughput. Moving on to cryptographic verification. Since we download these snapshots from random peers over the network, we need to verify all that data. We do this by calculating a 2048-bit set hash using the LT hash algorithm. Mathematically, a set hash works by hashing each element, in this case accounts, individually, and then combining these hashes. So we have a billion small hashes for each account. We reduce that down to one big hash. There's a very beautiful property here, which is that this is a homomorphic hash function. The reduction is mathematically commutative, so the order in which we reduce accounts doesn't matter. And this is the result of about half a year worth of work with a collaboration between Anway and Firedancer, where we replaced the previous hash tree-based version, allowing us to completely streamline the cryptographic verification with no sorting necessary to compute the set hash. We went a bit further though, so let's dive into the cryptography. Under the hood, the LT hash function or set hash uses the Blake 3 compression core. 99% of that algorithm is shown here on screen, but there's only 3 things that matter here, which is the 3 very simple mathematical operations that this whole hash function is made up of, which is integer adds, bitwise rotates, and bitwise XORs. So let's figure out the fastest way we can do these 3 operations on the CPU. And on x86, we use AVX512 to do this. We use the LVM machine code analyzer to see how fast these can run. The output looks a bit scary, but we'll break it down step by step. So the turquoise part here in the middle are the instructions, so VP add, adds numbers. The important part here is that these operate on ZMM registers, meaning that each instruction operates on 16 numbers at once. This is why it's called SIMD parallelism. Don't confuse this with Solana improvement documents. We have IPC, meaning we can do about 1.5 of these instructions per cycle. And if you run, the numbers, this is actually an insane amount of throughput. With a 4 GHz CPU, we can do about 100 billion operations per second per core, which translates to about 8 GB hashing throughput per second. But if we use the official Blake3 library, we'd get a completely different picture. Depending on input size, we actually have very low throughput. Here at the 1024 byte region, we know we're close to 8 GB a second. And the reason for this is that for SIMD parallelism, you need to lay out data in a very specific way. Computations are done in 16 lanes, but most lanes are actually idle. And the reason for this is that the Blake3 library chops up the input data that's about to be hashed into 1 kilobyte chunks. And if there are not enough chunks because the data input is too small, the high lanes are idle, which is performance left on the table. But even worse, the median account size in Solana is tiny, so there's practically no parallelism at all. We're just using 1 lane. Again, explaining here the graph. But this is one of the reasons why we've completely reworked a lot of the cryptography on Firedancer, including the Blake3 and LT-hash hashing libraries. We added special casing for the Solana dataset. We tune it for modern CPU architectures. And then using SIMD programming tricks like lane masking for this problem in particular, we were able to get the SIMD core to hash different accounts so that we don't have this lane idle issue. There are a lot of cool more optimizations that I could share, but kind of running out of time here, so I'm happy to talk about them off stage. All in all, though, we get about 4x improved throughput per core by tuning the cryptography under the hood. Well, the most important question, though, is how fast is it? At last year's Breakpoint, we took about 20 minutes to do a cold start. This includes downloading all the account data, hashing it, indexing it, verifying it. We got down to about 3 minutes. But wait a minute. In theory, we could do all of this in 20 seconds, since that's what the hardware allows. And if we look at, just a sec, our micro benchmark, we see that in isolation, each of the tiles performs at 20 gigabytes a second, which works out to about 20 seconds. What we see in the real world is something more like this, and I'd like you to focus on the compression part. This is to the aforementioned compression format issue, and this is how I'd like to end my talk. Firedancer will have to load snapshots produced by you infrastructure operators in the audience. There is a simple backwards compatible change that enables awesome optimizations on the snapshot loader side, namely enabling parallel Z-standard compression. With your help, we can push our, I think, already impressive startup speeds even further, get cold starts well under a minute. So yeah, that's snapshot loading. With that, I'd like to hand over to Philip, who will present algorithm work on Firedancer's replay dispatcher. Thank you, everyone. Philip, take it away.
Thanks, Richie. So this brings us to the last stage of booting a validator, replaying all the transactions that happened after the snapshot was produced. But replaying transactions is more important than just a validator boot, because the Solana validator is replaying transactions all the time, as Kevin mentioned. Last year, we showed a demo with the Firedancer leader pipeline producing blocks at 1 million transactions per second. But if the rest of the network can't keep up with that, well, then the chain can't actually do that. So in order to have a high-performance chain, a high-throughput chain, we need both fast leader pipeline and fast replay. And this year, I'm talking about the fast replay. But what even makes replay fast or slow? Well, as I mentioned, the Solana validator is receiving transactions all the time. In this case, say it's a transaction from Charlie to David, and Alice to Bob, and Alice to David. And it can replay these transactions in pretty much any way it wants, as long as the result is the same as having replayed them in the order that they're listed. So for example, it can replay them like this, serially, one at a time, very slowly. Or it could replay them with some parallelism, like this, which is faster. But if it tries to replay them like this, which would be faster, it'll get the wrong answer because it'll be replaying transactions that are accessing the same accounts at the same time, conflicting transactions. So it's the job of a component we call the replay dispatcher to decide which way to execute the transactions. It needs a way that's both fast and correct. And it needs to be careful to respect the conflicts and make sure it gets the right answer. And here's where the quality of the replay dispatcher can really shine. The faster we can churn through all these transactions, the faster we can execute them all, the faster we can submit our vote or catch up. And so while we could just use the trivial dispatcher, which executes them one at a time very slowly, it would get the right answer, but it would get there very slowly. And as we push Solana to higher and higher throughputs, leveraging the parallelism that's in the transactions becomes more and more necessary. All this might sound familiar. You might just be wondering why I drew all the diagram on the one side of the slide. And it's because it's really similar to another part of the validator that we've talked about quite a bit, which is the block packing. When our leader pipeline receives transactions, they come in one at a time, and we also have to decide how to execute them, potentially in parallel, before we send them out. And so you might wonder why the replay dispatcher can't just reuse the same ordering that the block packer produced, or why we can't just reuse the same code. It might seem a little funny that we go from serial to parallel, back to parallel, and then back to serial. But this sort of approach is actually pretty standard in computer science. When Richie was showing the code, you have a normal compiler which looks at your source code, discovers instruction level parallelism, but then outputs, again, a single linear stream of instructions, which then the CPU finds parallelism in and then executes. And it's standard because it buys you something very important, which is decoupling. So having to follow the block packer's parallelism is really constraining. What if we wanted to execute with more cores or fewer cores, or we could execute transactions faster or just some transactions faster? So basically, even if we knew how the block packer packed the transactions and we could encode it easily, we'd be better off just throwing out the results and discovering our own way of executing the transactions that's more finely tuned for our exact setup. And this means there's no way around it. For maximum replay performance, the validator needs to find a way to dispatch the packed transactions in a way that exploits possible parallelism. And it needs to do it very quickly. If we spend 100 milliseconds trying to find a special, using some super complicated algorithm to find a special way of dispatching the transactions that saves 10 milliseconds, well, that's a spectacularly bad trade. But as we saw, this task is pretty similar to what Pack has to do. So for the rest of the talk, I'll first give an overview of how we do it, and then I'll talk about two things that we learned while building the Pack component and how those apply to the replay dispatcher, and then I'll show some results and wrap up. Okay, diving first into the algorithm. So the standard approach for a problem like this is DAG scheduling, directed acyclic graph scheduling. So we represent each transaction as a node on the graph. You can see the three transactions from before and adding a fourth transaction for good measure. And then you add edges to represent the conflicts, transactions that can't run in parallel. And then you run a pretty simple algorithm. You look at the transactions that have no incoming edges, I've circled those, and those are the ones that can be executed right now. And then as they get executed, you delete the node and its edges, and you just repeat this until you've finished all the transactions in the graph. There's basically only two details left to work out: how to represent the graph in memory, and then when you have multiple transactions that are ready to be executed, how you choose which ones you execute. And actually, these are the two questions that our work on Pack helps us decide. Okay, first diving into the question of how to represent the graph in memory. And the way we represent it is mostly a question about CPU caches. Richie was talking a lot about that as well. And they're key for performance. And when we found that when we were building Pack, the code spent a lot of time waiting for data from memory or from lower levels of cache because we had such a large working set that we had churned through the whole data between accesses to data. So the data that we wanted was no longer in cache because we had accessed so much other data in between. So we knew that the representation was something we needed to put some thought into. And one of the things we found when building Pack is that actually most of the bytes in the transaction don't matter for dispatching, which means that if we're clever with how we represent the data, we can actually store a lot less than you might think. And that will reduce cache misses. So let's quantify this. I looked at about 25 million transactions in a recent day in mainnet. And what we found is that there's actually a lot of data that we can ignore, or as I mentioned. The signatures, the recent block hash, all the instruction data, all this, of course, matters for executing the transactions, but it doesn't matter for dispatching them. So the first optimization is just not to store any of that data in the data structures that matter for performance. But that still leaves this huge section, the address lookup tables and the addresses themselves, frequently called pub keys. And these actually are needed for dispatching because these are where the conflicts are found. And you can see it is actually the biggest field. But again, when we were working on Pack, what we found is that even though these addresses or pub keys are big, 32 bytes or 256 bits, from an information theoretic perspective, the information that they encode is much smaller. It's something around 11 bits on mainnet and for a typical pub key. So the next optimization we employ is to map all of these pub keys from the big 32-byte string to a small index, and then even then, only store the index when absolutely necessary. This mapping is trickier to get right because you have to make sure that even in a worst case, you don't have any mistakes. But we did the work and we have everything carefully bounded, and we know that it will, even a worst case block can't trip this up. Okay, but even throwing out all the data that we don't need, there's still a lot of cache misses. So the second way to optimize cache misses is to pay close attention to how we pack values. Because when you load a value from cache, you get a whole line, typically 64 bytes, which means that if you access a nearby value, it's typically free because it's in the same cache line. So let's show a diagram of how we're representing stuff in memory. In this diagram, each column is a cache line, and on the left is how we represent it in our replay dispatcher, and on the right is how you would maybe represent it if you're just writing code without trying so hard to minimize cache misses. And let's suppose we want to do an operation like iterate over the edges and update some metadata. So the first thing that we would do is maybe load the metadata. And then you load the edge count. And then you load the edges. Nothing's too surprising here. With our way of packing the data, we can store about 13 edges in the same cache line as the metadata and the edge count, which means that loading the first 13 edges is basically free. But if you're representing this in a more normal programming language, the first thing you do is dereference some pointer and the vector, say, and that gives you another cache line. And then you load this other cache line, which has the actual edges. And since if you weren't doing the work to squeeze these pub keys down, they'd be larger. So you would only say 4 account addresses in each cache line. And then finally, you would write back the metadata. So iterating over the average transaction goes from like 3 cache lines down to 1. And since cache misses are so key for performance, this is actually a really significant difference. It's worth mentioning that in order to use a representation like the one we're using, you also need to bound the number of edges, which requires some careful transposing, I guess, or careful representation. But you can already see the benefits. Okay, that wraps up learning 1. Common wisdom is that in a graph algorithm, cache misses are inherent because of lots of random accesses. But what we see is that with careful coding, we can actually reduce the cache misses a lot and improve performance. That brings us to the second question, the second detail to work out. When we have multiple transactions that are ready to be executed, which one do we execute first? And flashing back to our toy example from a few slides back, in this case, we had 2 transactions that were ready to be executed. And actually, in this case, they're both equally good. But if instead of CD, we had CE, you could see that at the start, we would still have 2 transactions to execute, but CE would be less beneficial towards finishing the block. Because when we finish AB, that unblocks AD. But when we finish CE, that doesn't unblock anything. The precise way to think about this is in terms of the critical path of the graph. The critical path is the longest path through the graph measured with the appropriate weight. And it's important because no matter how many parallel resources we throw at the problem, no matter how many cores we're using to execute this, it's not possible to finish the graph faster than it is to execute the critical path on a single core. So the way to finish replaying the block as fast as possible is to focus our execution resources on the critical path whenever we can. When we were building Pack, we spent time getting familiar with the structure of these graphs in real mainnet blocks, and we also saw there how important the critical path is. But you might remember that we're actually executing these transactions and receiving them in a stream. We want to start executing them before we've received the whole graph, so we can't wait, build the graph, analyze it, find the critical path, and then start executing. We want to start even before that. So we turn to some heuristics. Certain accounts are hotly contended. So if a transaction accesses one of those, then it's much more likely that another transaction is also going to be executing it, and then those two transactions will be on the critical path. Other accounts are much less likely to cause contention, and so those transactions are probably not on the critical path, so we can wait to execute those. So as we insert transactions into the graph, we're measuring over many blocks how frequently transactions are executed. And then we can just use, based on our past history, we might guess that, for example, C and E are hot, A is pretty warm, and C and E are not hot, they're cold. A and B are hot, and B might be warm, D is extra hot, and then we can use that to color the transactions when we're comparing them. So then we would know to pick the transaction involving A and B, because they're hot accounts, before we execute C and E. And we can make this determination, before we even receive the transactions in the rest of the graph. And the best part of this is that all this metadata fits in the same cache line as the node itself, so we get this basically for free with no extra cache misses. And that wraps up warning 2. To execute a block quickly, we need to focus on transactions on the critical path. Okay, now let's move on to some results. Michael and Anway are going to show the fruit of all this work in a few minutes, but let me show 1 or 2 graphs that summarize everything. On the x-axis, we have the number of cores we're using to execute transactions, and on the y-axis, we have the simulated time to execute the block. Here, the simulator uses the real replay dispatcher code, but simulates execution of the transactions. So what we see is that the graph at the beginning is decreasing, which means the replay dispatcher is finding parallelism in the block. But then that only goes up to a point. After about 3 or 4 cores, we hit the critical path. And basically, we're constantly executing transactions on the critical path, so more parallelism hardly helps. And thirdly, if we zoom way in, we can see what was just a speck before is this is the red section, which shows how much time is spent running the replay dispatcher, not executing transactions. And the light red is when the replay dispatcher is busy, but it is also executing transactions at the same time. We can see that the replay dispatcher is mostly idle, and these are executing mainnet blocks faster than real time. That means the replay dispatcher can handle much more, much bigger blocks and much higher transaction loads. Okay, finally, I want to show a similar graph taking from a smaller data set. We can use an integer linear programming formulation to get a bound on the best possible execution over all ways of executing the blocks. Well, this form of computing it is extremely computationally intensive. For small blocks, it takes tens of minutes or even hours, and sometimes it still doesn't even converge. But I've shown this bound in the line. And what we can see is that even in less than a millisecond for these blocks, we're getting close to the theoretical average, or theoretical optimum of the best way to execute these transactions. You can see it's quickly choosing a way of dispatching transactions that's close to optimal. Okay, in conclusion, echoing some of the themes that Kevin mentioned, we're here grinding away on tiny details, worrying about cache misses and how data is laid out, and learning from our past experience to make our code even better. We're doing it so that we can keep making Firedancer and Solana faster and faster. Now we'll turn it over to Michael and Anway, who are going to show all this code in action.
All right. Thank you very much. So you guys have seen a lot of the cool stuff we're doing, how we're optimizing the validator to make it super, super fast. You're probably pretty excited to see it in action. So Anway's going to do what I would call a proof of restart here. We're going to restart a validator live in front of you and boot it up. Here you have it. A fresh, from-scratch validator, written entirely in C. It's running live, highly staked, and on mainnet. There is not a single line of Rust code running here. Yeah. This represents a lot of work by the team, countless years of nights, weekends, a lot of hint waters, Diet Cokes. The GUI we're showing you, if there's any operators, validator operators watching, we kind of built it for you. The software is sophisticated, complex, it's got a lot of moving parts. Kind of think of it like an airplane. And these operators are something like pilots, right? We want to teach them with the instruments we have how to operate it well, so they can make the network faster too, and also help in an emergency. If anything's going wrong, to quickly diagnose and see what went wrong. Here we booted into the snapshot loading screen. Richie talked a lot about this. And we're booting this snapshot in real time. You can see the pipeline parts of the system running on 3 CPU cores here. Where we're getting the snapshot from, we're actually downloading this from the network, from a live peer, decompressing it, and inserting it into our accounts database. See, it's about halfway done. Should take around 2 minutes. I'm going to briefly explain what you'll see after this, because it's going to go by pretty quick. Once we finish loading the snapshot, we have to catch up to the chain. We fell a little behind as the chain kept moving forward from the snapshot. So we'd have to repair and replay. On this screen, so we kind of start a bit behind, and we're going to aggressively start catching up. Right before that, actually, there'll be an incremental snapshot. So there's kind of 2 snapshots we have to load, a full and an incremental. You see we're doing about 3 gigabytes a second of output, and inserting a little over 6 million accounts. Yeah, and here we're bottlenecked on this insertion stage. We'll watch for a second in silence while we wait for this. And again, we'll see really quickly the incremental snapshot, and then repair and catch up, which is a lot of what Philip talked about. Hopefully we'll catch up quickly. There's the incremental. And here we're catching up. So here you have Firedancer, a lot of information all at once. We have a bunch of new visualizations we're excited for you guys to see. Slots, right at the top. This shows the validator is keeping time. It's on pace with the chain. It's not falling behind. You've got your turbine slot. This is the tip of the network. And our process slot, which is falling right behind it. We're routing well. And you can see we have a leader slot here. It's a pretty highly staked node in about 1.5 minutes. This slot's visualization is really good just for making sure your validator is healthy and nothing has gone wrong. Below this, we have shreds. I think the Solana network has kind of intricate and beautiful protocol underneath it. And a lot of what we're doing here is trying to show you inside the validator to help you understand. I want us all to kind of just sit and stare at the shreds thing for a second. I'll explain it after. I think this is kind of art. If we're talking about slots, each one of these vertical columns represents a slot produced by some other leader on the network. This is live, real time, that they produced. And every row within that vertical column is a network packet they had to send to us for us to replay that slot. So these are the shreds. We're showing us receiving these shreds, replaying them in green. Here you can see a little red. This means the validators had to do a repair. That's pretty rare, so this is showing the validator is healthy. I'll point you again, time until leader, about 10 seconds. So we're about to produce a block here. And hopefully we'll see that go well. So this is a live mainnet block. We'll prove it to you. go to the leader schedule, and we'll grab this slot number. And we'll just pull it up in Solana Block Explorer. Feel free to do this on your phone. There it is, just on the chain about 30 seconds ago. It's well packed, the chain's not at capacity, but you can see if we scroll down, this is DNVZR validator. And we put a bunch of stuff in it, a lot of votes, a lot of transactions. If we go back to the validator now, and we'll go back to the overview, continue showing you a few more things here. So a lot of you might have seen some of these visualizations. These are for Firedancer. This is representing the leader pipeline in motion, building up to whenever our next leader slot is. But we'll keep scrolling down and show you a few other new things. Here is every part of the Solana protocol, live running, network and egress that they're taking up. You can see repair here operating pretty easily with the TPU, Gossip, Turbine, our metrics system. If we keep going down, this is a bit of a more interesting section. These tiles, we refer to these are really CPU cores of the system, showing how busy it is, what each CPU core is doing. If you scroll down a bit more, you'll see there's a lot of these, but they're mostly idle. Firedancer is massively over-provisioned. We've designed it to do 1 million TPS, and it would, if it could. So these exec tiles, we have about 6 of them. These are actually executing the replayed transactions. So as blocks come in here, these are executing transactions, as Philip showed you from that dispatcher, and these are pretty much idle. Yeah, so validator is just unchallenged right now. If we scroll back up, I think, another leader block there. OK, we'll cut over to the slot details, actually. So we'll pull up one of these leader blocks we produced. We're going to show you a little information about it. Here is the slot detail information for the block we produced. Pretty detailed. We're showing you a bunch of information here you might find useful. Protocol limits, busy accounts, cumulative execution time. Our goal with Firedancer is to make the execution incredibly, incredibly fast. And so we have a ton of detailed information here and metrics for making sure that happens. Keep going across. We have all the fees in the block, income, where it came from. Is it a bundle? Is it a transaction? And then performance. So we talked about the scheduler as one of the most important parts of the system. It often represents a bottleneck. So here we're showing all the decisions the scheduler took throughout that block, why it took it, how many transactions were in your buffer, and a bunch of other interesting metrics about the block. We keep scrolling down here. I'm going to try and show you something interesting. We get to the bottom here. This is what we call the banks visualization. This is showing what every CPU core did that was executing transactions for this block and which transaction it was doing. So we're going to filter this to just the votes that went into the block and just those that were successful. And remember, this is a block we just produced live. We're going to take a look at the first few votes we received. And with any luck, not that one. Here we go. This first one is likely someone voting late on a prior slot. But here, this vote we received is from this interesting-looking validator, FBBQ. Might be wondering how this guy vote so fast. Took him 26 milliseconds. A little bit of a secret, but we'll reveal it to you. This is Firedancer too. So we run one other node, and it is the fastest voter on the chain. Just to explain what goes into that, voting quickly involves every other part of the validator that wasn't in Firedancer. We have to receive shreds, replay them really quickly, come to consensus, cast a vote quickly, send it out. We're able to do all of that in 25 milliseconds. You can see here kind of the rest of the cluster and about how long it takes on average, and us with our sample size of 1. Wouldn't be fair to just take a sample size of 1, so we're going to show you a bit of a bigger one. As part of building Firedancer, we wanted to track data and compare all the validators, and we couldn't really do that easily, so we built an entire reporting site of our own. Here, you can see we just added a few days ago Firedancer. So you'll be able to track the deployment and rollout of the validator as we make it better, add more stake. But here, we're going to go to the daily view. This is showing literally today or yesterday. We're going to sort by an interesting metric we call lat1 vote rate. This is the percentage of time the validator voted on a block in the very next block. This is the quickest you can possibly do it. And you'll see the #1 validator yesterday was us. All right, we can go back to the validator. We'll just show you one other thing here. There's a ton of components involved in running the validator. We've implemented all of them. Repair, gossip, snapshot, load, a ton of stuff we don't have time to go into. We'll show you one more screen here. Gossip, this is kind of one of the more interesting components of the network. This is the first thing you have to do when you boot. Gossip is a table of information we have to get from other validators about their IP address, where they're located, what snapshots they're serving. Here you can see the whole gossip network live in action, who we're receiving from, who we're sending to, what the bandwidth is. If we scroll down, how much data we're storing, what types of information we're storing in this table, and here we keep going down. Just seeing that it's healthy, we're not receiving too many duplicates or failed data. And here is every other peer in the cluster that our validator is connected to and receiving live. This table infinitely scrolls, it's updated in real time. We're pulling a ton of information to allow us to diagnose and debug stuff quickly and make this validator really, really good. One other thing that's kind of interesting, this UI is live. You can view it yourself, gui.firedancer.io. We'll leave this validator up and running today for a few hours so you can take a look. I want to close with a couple of remarks. Well, the talk is called When Firedancer. And as Kevin said, if you look kind of at what we did with Firedancer, we were at 0% stake last breakpoint, and now we've got up pretty high. I think the deployment trajectory is going to look pretty similar for Firedancer. We have 0% stake now, effectively, but it's about to go up. But people kind of think there's going to be this big bang moment with Firedancer, where one day it's not deployed, and the next day it is. And reality is like kind of nuanced. The chain is not at capacity. So when Firedancer ships, probably nobody will notice. In some sense, when for Firedancer was 3 years ago, right? It's when we started contributing to the core protocol, started hosting performance meetings with Anza, started putting our design in, bringing our technology over, and contributing all to the community, open source and free. The chain is already, in a lot of ways, a product of Firedancer. We'll finish with an anecdote. When I started it on the Firedancer project, I was chatting with Kevin Bowers. And I asked him, well, this technology is really valuable. We have a lot of expertise in stuff we're doing. And we come here and we give it open source and give it away for free. Why? And he said, well, I've found in my experience you can put up barriers and try and prevent people learning what you're doing and hope that that keeps you ahead. But it doesn't really work. The best strategy I've ever found is you just run faster than everybody else. And I hope that's what we're doing with Solana, what we're contributing here. So thank you for coming.
So you obviously like this video enough that you've got to the end. That's quite a big task. But listen, do me a favor, hit the like and subscribe button, and also check out what video's next, because I think you'll love it. But if you want even more, and when I'm talking more, I'm talking about member-generated ideas, incredible alpha, research, everything there to help you in your journey, just head to realvision.com/join for the best financial intelligence out there and the pure alpha that's within the platform.